Good afternoon. I'd like to start off with saying I'm David Carr. Happy Veterans Day to everyone. That's why I have my American flag behind me. I wanted to start off. This would be my first video to lecture with, so bear with me. I want to make sure, first of all, that you're watching this video as one of my students from Planetary Geology at Wayland Baptist University. This is going to be on Chapter 2 in your textbook, the 7th edition of The Cosmic Perspective by Bennett and Donahue. Chapter 2 in this lecture will also be accompanied by the lecture slides that I have provided to you on Blackboard. So if you haven't done so already, pause this video and go to Blackboard and download the lecture entitled Chapter 2 under Content Area, Week 2, Chapter 2. Download that so that you can have that up as I go through each slide. Now, assuming that you have downloaded the slides and you're ready to go, I'm going to go through each lecture one by one, each slide one by one. It should take approximately 1 hour, and then you will be able to stop, pause, come back whenever you like. Alright, so here we go. I like to quote some scripture every once in a while. This one is on your first slide, is Proverbs 16:32. He that is slow to anger is better than the mighty, and he that rules his spirit than he that takes a city. We're talking about the entire universe in this class. That takes time. How was it made? How was it formed? That takes time to explain. Do we actually understand how it was made, how it was formed, how we came to be? No, I don't think we do. That's my personal opinion. And yet, do we have the capacity to understand it? We probably do, but it takes time. Okay, moving on into the second slide. FERPA is the family education, and I believe it's a very important act of Congress to make sure you're aware that when I send information out to you, you have to understand that I am only by law allowed to use the Wayland email accounts. So make sure your Wayland email accounts are active. By the way, you can once you make sure they're active, you can always forward any Wayland email accounts to any email address that you would like. So you can forward it to your phone, your iPad, to your Hotmail, Yahoo, ATT address, any address, Gmail, that you would prefer if you want to combine all of your emails, which is fine. If you send me an email from your personal account, that's fine, no problem, and I will respond accordingly. As a matter of fact, I forward my Wayland email accounts as a text to my phone, and that way I can get notified right away that you sent me something, you or anyone. Now, because I'm a cheapskate and I don't have data on my phone, I just get a text. I won't be able to open up your attachments. So do not send me attachments. Only send me a text or an email message. I will reply that way. If you need to send me a research paper, any assignments, if you need to attach something to, like an extra credit article, do not send it to me by email. Go on Blackboard and submit it through Blackboard. Okay? If there is no way that you can find to submit it on Blackboard, email me and ask me how to do it. Okay? Because I will make sure that you do it only on Blackboard. Okay, moving on. I have a link that's on my laptop for a particular humorous video, and we're going to skip this slide. It's called Face the Rear. It's all about peer pressure. My point here is, if you're concerned about peer pressure, if you have a question and you think everybody else knows the answer, no they don't. No they don't. Hey, even at my regular job, I'm the one that usually asks the questions, knowing that, it's a stupid question, but there's probably somebody else that has the same question, or they're asleep, they're not thinking, they're thinking about their day or what they have to do tomorrow. So I ask a question, and it brings everybody back in. So you ask those questions. Even maybe I will think that they're a stupid question. Don't be intimidated by that. It's my weakness, I won't dress you down though. Don't worry. So when we're in class, don't worry about it. Okay, next slide is just a quote from Mark Twain, discovering the universe for yourself. He said, we had the sky up there, all speckled with stars, and we used to lay on our backs and look at them and discuss about whether they was made or only just happened. You know. So Huckleberry Finn in Mark Twain's book, was wondering, what's going on up there? How is it made? Or did it just happen? That's what we're going to talk about in this class. So in the next slide, we're section 2.1 of these slides. Patterns in the night sky. You've heard of constellations before. We'll talk a little bit about them, how they're located up there, the fact that how are they rising and setting, and what about the entire year? What do we see up above us the entire year? In the next slide, you'll see that a constellation is a region of the sky. And let me make it easy for you. A region of the sky means 88 constellations. 88 constellations up there. Let's say, for example, that Texas has 88 counties. The state of Texas has 88 counties. Well, I'm in Bexar County right now. You might live in Comal or Kendall County or Guadalupe County. Some people may live in Wilson County. You know where those counties are. Kendall County. You can think of all kinds, at least 88 counties in Texas. You know where they are. The ones that you're thinking of. You know where they are. So, where are they? Well, I'm in Bexar. Guadalupe County is just slightly north of me, northeast of me. Kendall County is slightly north of me. Wilson County is about south of me. I know where they are in relation to myself. And that's what a constellation is. If I tell you that I'm looking at Betelgeuse, for example, on your slide, in the Orion constellation, that means a location in the sky, and that's it. It's just like a county. The other thing is, using my analogy of counties, all counties have different boundaries. They're all weird looking boundaries. So are constellations. Constellations have extremely weird boundaries. So, same idea. Orion is always going to be next to Canis Major, another constellation. Thus, that's why I use the idea of counties. Okay, 88 constellations in the sky. Moving on. So let me make sure you're on the right track. Think about this. The brightest stars in a constellation. What? Do they fall? Are they in the same star cluster? Do they lie at about the same distance from the Earth? I'm talking about the very next slide. May they actually be quite far away from each other, and the next slide shows you that the answer is that it's worth pointing out that two stars in the same constellation can actually be farther apart than stars on opposite sides of our sky. Depending on their distances, for example, Procyon and Alpha Centauri are much farther apart than Procyon and Betelgeuse. But in space, Alpha Centauri and Procyon are both relatively nearby stars. Their distances are 11.4 and 4.4 light years respectively from us. Okay, 11.4 and 4.4, which means they're not more than about a dozen light years apart, while Betelgeuse is several hundred light years away from Procyon. A distance to Betelgeuse is about 430 light years. Okay, moving on to the next slide. I'll take you there to the celestial sphere. So, thinking about all these 88 constellations and the fact that not all of them are close to each other, I want to use a little history to explain where we came from as far as looking at the stars. The celestial sphere was developed by the ancients. The ancients looked at the sky and noticed all these stars, and they did not realize that the earth, first of all, was rotating. Did not realize, second of all, that the earth was orbiting orbiting the sun. And third, they didn't realize that all those stars up there were different distances from the earth. With all that in your mind, keep that in mind. Realize, put yourself in their shoes, thinking about God. God is perfect. What He does is perfect. We have perfect circles. God created man on the earth. The earth looks at the sky and sees the stars. All the stars, in their view, orbit the earth. The stars, including our sun, are orbiting the earth. The earth is the center of this celestial sphere, the center of heaven, in the heavens. Okay? The earth does not rotate. Everything else is orbiting the earth. All stars are the same distance from the earth, and they orbit the earth in a perfect circle. The sun, being just one of many, orbits the earth approximately 23.5 degrees tilted from with respect to our north and our south pole. Okay? And that's where we head. We have the north celestial sphere directly above our north pole. South celestial pole, I should say, directly above our south pole. We have the celestial equator, which extends, if you can imagine, extending our equator infinitely throughout the universe. That's what the celestial equator is. In the ecliptic, imagine extending the imaginary line or an imaginary circle that the sun etches as it rises and sets around the earth. That's the imaginary arc, if you will, that is extended out infinitely. That's called the ecliptic. Ecliptic, and we'll talk about that word later. It's also very useful to bring a model like this celestial sphere to class to give you an idea, but we're not in class, so think of a beach ball, if you will. That looks kind of like the object, the celestial sphere on the slide, kind of looks like a beach ball. That's the idea. And you show all the, you can think of that beach ball when you think of the celestial sphere. Next slide goes a little bit farther with the celestial sphere and draws the constellations, all 88 of them. You see that when you look at one side of the celestial sphere, you don't see all 88 constellations. Some of them are on the other side, right? And you see the North Pole, the South Pole is down under, and you see the ecliptic, noted as those yellow dots. That's the sun rising and setting around the earth. So we don't have a model to show you, to bring to class, since we're virtual here, but you might want to think of this slide. Probably need to skip it because we can't go any farther with it, but just think of all the constellations and where they are. See how one's next to the other? They're always that way, just like counties. Okay. Now, moving to the next slide. One of the most beautiful objects in the sky are groups of stars called the Milky Way. Groups of stars, organized stars that orbit a center we don't really know much about. We know a little about, but it orbits a center. These groups of stars we call the Milky Way. And in these groups of stars we call it a galaxy. The Earth, is inside this Milky Way galaxy. And this Earth that we live on is part of a system within the Milky Way. We call it the solar system. The solar system, okay? But the Milky Way is a band of light making a circle around a celestial sphere. The ancients did not think of the Milky Way like we think of the Milky Way now. They thought of that group of stars orbiting the Earth. Alright? You may never see the Milky Way, actually take a picture of it, because we have never, until recently, completely left the Milky Way. Voyagers now cross that line. And we'll probably never physically, personally see it. But this photo is worth showing. And we use the term Milky Way in two ways. It's a band of light in the sky, and you can't really see it from San Antonio. You have to go out into the hill country, for example, where there are no lights, no street lights, no lights whatsoever, no car lights, nothing. You might be able to see a blanket of stars on a clear night. So the two meanings, the band of light in the sky or the galaxy, they're closely related. We like to use the following analogy: so we can imagine being a tiny grain of flour inside a very thin pancake, or like a crepe, and the pancake is bulging in the middle and a little more than halfway toward the outer edge. Okay? So what do you see if you look toward the middle? You see dough, probably, right? So if you look toward the far edge, uh, you see dough, right? You're inside the dough, the earth, okay? So similarly, if we proceed that way, you'll soon realize that you'll see a band of dough encircling your location, all right? But if you look away from that plane of dough, that pancake, above it, below it, right? Not edge on, but above it or below it, you'll see, if you were able to grasp it, you'll see a very thin layer of dough, the pancake, all right? And then you'll see the universe beyond it. Okay, that's what we do. That's what we do. Next slide will show how we locate objects in the sky. Okay, we have to locate them in certain ways while we're inside this pancake or inside this crepe. We have to use reference points. We move from that celestial sphere to the local sky. The local sky looks like a dome, if you will, and that beach ball, because we see only half the celestial sphere. And if we want to locate an object, it's useful to have some reference points. Students, you'll usually probably already understand the horizon and the cardinal directions, but I need to probably explain zenith and the meridian. Right? A simple way to define the meridian is as imaginary half circle stretching from the horizon due south through the zenith to the horizon due north. Let me back up and explain. Cardinal directions are your latitude and your longitude. Alright, just think of the latitude and longitude. And then your zenith, directly above you. Your meridian, it's shown in that slide there. Your meridian is, let's say the sun rises in the east and sets in the west. If you were to draw that imaginary line that the sun takes, or the imaginary arc that the sun takes, that is a meridian. Okay, that arc, if you will, rises in the east and sets in the west. Okay, so you have 360 degrees of meridians, right? If you just go all the way around with your finger pointing at the horizon and just draw a line over your head, over your zenith, and then all the way down to the other side, that's a meridian. The prime meridian is the line that goes from the horizon up to the zenith, and as it goes from the horizon to the zenith, it goes through Greenwich, England. That's the prime meridian, or 0 degree longitude. All meridians are longitudes. All latitudes are 90 degrees of the longitudes. The 0 degree latitude line is the equator. Okay? The equator. If I move north of that latitude line, I will be moving north latitude. If I move south of the equator, I'm south latitude. That is also defining the division between the northern and southern hemisphere. Okay? San Antonio is approximately located in these cardinal directions: 30 degrees north latitude, 100 degrees west longitude. Alright? However, if you look at an object in the sky, you specify its altitude as well. The altitude above the horizon and the direction along the horizon. A good way to reinforce this idea is to pick an object located in the classroom or in your wherever you are watching this lecture. So which way's north? First of all, you have to know which way's north, and then you have to estimate the altitude and the direction. Okay, you got to know where you are. We have GPSs that tell us where we are now. And then you need to know the altitude of, say, a picture on the wall, or the corner of a wall, or the corner that meets the wall and the ceiling, like this, that corner. How many degrees up from your supposed horizon, right? Next slide is going to give you an idea. Let's say you pick a picture on the wall, or a dot on the wall from the floor. Let's say the floor, where the floor meets the wall, is the horizon. And then you have to determine how far up that dot on the wall, or whatever you picked, how far up from the horizon it is. Alright? First of all, you know where you are, your latitude and longitude, and then the direction that you're looking. I'm looking north, or northwest, or southwest, and then how many degrees up to that location that you have spotted. Alright? We use angles from that point. Your reference point, horizon, up to that spot. So you point out in that general way, no judging, there's no specifics needed, It's like an illusion of stars lying on the celestial sphere. It's due to our lack of depth perception in space. We don't really know how far away it is at this point, but we can measure the angular size from horizon up. Okay? From that, we can determine the distance that object is from us. We have to take a little bit more time to explain that to you. Okay? Alright. But on the slide, you'll see that if you use your fingers, your finger, like your index finger, is approximately 1 degree. If I start from the horizon up, 1 degree up. If I use my whole hand, it's put my pinky, use my eyes to point my pinky toward the horizon, and then up to the top. From that distance up the wall, for example, is 20 degrees. And then if I use my fist, another 10 would be 30 degrees. So something like this, right? That would be 30 degrees up from a horizon. And that's how we determine an object in the sky. Say you want to call your significant other in another state, say New York City, and you want to look at the same star at the same time that evening. So you call each other and you look at the North Star. The North Star is in the north, and it's approximately 30 degrees above your horizon, and you can both look at it, right? How romantic. Okay. So we look at all angles that way, all stars that way. And if you think of some simple ideas to get more accurate, we have to be more specific than degrees. We have to uh, divide up 1 degree into several different sections. And the way we do that in astronomy or in planetary geology is we use arc minutes and arc seconds. 1 degree is 60 arc minutes. 1 arc minute is 60 arc seconds. Let me make sure you understand that. The angular size in the next slide, the angular size of your finger at arm's length is about 1 degree. How many arc seconds is this? Well, the answer is not 60 arc seconds because 60 arc seconds is 1 arc minute. The answer is not 600 arc seconds because that's bogus. Alright? The answer is 3,600 arc seconds because in 1 degree you have 60 arc minutes, and in each arc minute you have 60 arc seconds. 60 times 60 is 3,600 arc seconds in 1 minute. Okay? Now, looking at the next slide, it's entitled "Why Do Stars Rise and Set?" Well, first of all, let me tell you something. We've always been told that the sun rises in the east and sets in the west, and I'm not going to change that thought process. But I want you to understand something, that is incorrect. It's technically incorrect. Nothing rises and sets. Nothing. But we still use that in astronomy because the ancients never considered the earth rotating. Everything rises and sets. The fact is, the earth is the thing that is moving, not the objects out in space when we say rise and set. Specifically for this, rising and setting. But most objects rise in the east and set in the west, generally. Not directly, not exactly, but generally. The moon rises and sets, rises in the east and sets in the west, generally. Venus, Jupiter, all objects. Okay? The sun, all objects in space. It has to do with the earth, not those objects. They rotate east to west, so the stars appear to rotate the opposite direction. Okay? Earth is what's rotating east to west. You with me? And all the other objects are just moving the other direction. Okay. So to answer the question is very simple. We look at the celestial sphere from the outside. But of course, we're looking from our location on Earth, which makes the motions of stars look a little more complex. Alright? If you notice at the celestial pole, the North Celestial Pole, some objects will appear to make a complete arc in one day. Complete arc. And we'll get to that in just a sec. Alright? Moving on to the next slide. Our view from Earth can be explained by noticing that the ancients didn't realize we were moving. Okay? But we can't see stars near the. We can't see stars. There's some simple things. We can't see the South Celestial Pole stars from San Antonio, Texas, from the northern hemisphere, for that matter. All stars rise in the east and set in the west. Okay, moving to the next slide. So here's a question: if I was standing upright and I was looking directly at the arrow on that beautiful object, that rock formation, and I was looking directly at that, you see all those circular lines. Those are stars using time-lapse photography. They're stars that are orbiting completely. I can see those stars even in the daytime and in the nighttime, is what that's trying to tell you. Okay, and if I'm looking right at that direction, what is the arrow pointing to out of those choices? The arrow in the next slide is pointing to the North Celestial Pole. Okay? The North celestial pole. If you do not understand that, come talk to me at class when we have class. Or email me. I don't get it. It doesn't make sense. You're wrong. You're smoking something. Whatever you want to say, just come talk to me. Next slide is, why don't we see the same constellations throughout the year? Well, and obviously we have two basic reasons here. That the visible constellations, they vary, but we're going to explore each one. Okay? We're going to explore each of these reasons. The latitude varies, the constellations vary with latitude, and the time of year, the constellations vary as the Earth moves throughout the year. Okay? Remember, the ancients didn't realize the Earth was moving, so I'm trying not to consider the Earth moving at this point. Okay, next slide regards the cardinal coordinates that I just mentioned, and I just wanted to make sure you were aware of them. How do I remember each one? Well, the latitude, first of all, are the imaginary arcs throughout the Earth that start at the equator and either move north or south, and they are horizontal to the equator, parallel to the equator. And I say flat, flatitude. That's how I remember one from the other. Flatitude. Put an F on the front, okay? So this is a brief review of latitude and longitude. It's also useful to bring I could bring a globe in, but I don't usually. And the photo at the right is the entrance to the old Royal Greenwich Observatory near London. The line emerging from the door marks the prime meridian. Okay, those are the longitudes. Alright, next slide is the sky. It shows that it varies with latitude but not longitude. The sky varies because we are moving up in our direction. It varies with latitude but not longitude. Okay? Altitude of the celestial scroll is equal to your latitude. Alright? North celestial pole, south celestial pole. In the northern hemisphere on the left we see the Big Dipper. And I'll point that out to you. And the Big Dipper, as you can see, points to Polaris. Polaris is what we call commonly the North Pole. And in the southern hemisphere we don't see the North Pole. In the southern hemisphere we see the South celestial pole. But astronomically there's nothing there to see. So we use something else called the Southern Cross to point to it. And you'll see no matter what time of the day it is, the Southern Cross points south, generally south. And on the left, no matter what time of the day it is, the Big Dipper, the last two stars in the figure there, point to the North Pole. So we can always know which way is north and which way is south, east, and west, no matter where we are in the world. Next slide is the stock question. The North celestial pole, the North Pole, Polaris, is 50 degrees above your horizon. Due north, where are you? Well, you're at your latitude of 50 degrees north. Okay, that's how you know your latitude. Next slide is the sky varies as Earth orbits the Sun. So the Earth orbits the Sun. It appears eastward along the ecliptic, and at midnight the stars on our meridian are opposite the Sun in the sky. One misconception is the stars go away in the daytime. No, they're still there. They're still there. It's just that the Sun is so bright it blots out anything beyond that shine. Next slide is a very special topic about the length of a day. We always say one day is 24 hours, but we also go further and say that equates to a full rotation of the Earth. Okay, that is not entirely correct. One full rotation of the Earth is called a sidereal day, and it is 23 hours and 56 minutes. If you notice in the figure there, I have to leave it to you, since this is online, I'll leave it to you to look at this figure to notice that if you go one full rotation, you do not completely come back to the Sun. You have to go another 4 minutes in order to completely go back to the sun. So, thus, we have a 24-hour day. Okay. Then, next slide is a little recap of what we've learned. We talked about the regions of the sky and how we locate objects in the sky. Um, why do they rise and set? Um, and why don't we see the same constellations throughout the year? Um, I do have sometimes I do some humorous things in class. The next slide is about a pump, but I don't want to take the time. I don't have the link for you virtually. Okay, so we'll skip that slide and go to section 2.2 of our lecture, and we'll talk about the reasons for the seasons. Okay, what causes the seasons? How are they marked in their progression? And how about the orientation of Earth's axis? Does it change with time? The next slide is a thought question for you. Is it true or false that Earth is closer to the Sun in summer and farther from the Sun in winter? And the answer is false, right? Earth is closer to the Sun in the summer. No, that is wrong. Earth is farther from the Sun in the summer. It is closer to the Sun in winter. Do you understand that? Earth is farther from the Sun in the summer. Alright, next slide shows you. The seasons are opposite in that shows you the answer to that question, so the answer is false. And I'll go to the next slide to show that the seasons are are very important to us. They're different from one hemisphere to the next. If it's wintertime in San Antonio, it's summertime in Sydney, Australia. Okay. If it's fall in San Antonio, it's spring in Sydney, Australia. Alright. So you might optionally mention or think about this. Alright. When you think about the hemispheres. Where are you? It is the reason why we have the tilt. The reason why we have seasons is the tilt of the Earth. It has nothing to do with the distance the Earth is from the Sun. We just happen to be the right distance from the Sun to have seasons. So next slide is what causes seasons. Alright. What causes this slide uses an interactive version. If you have the online tools to your book, you can take advantage of this interactive version. It appears in your book. It's the following, and it uses frames from the seasons tutorial. You could go to the tutorial in masteringastronomy.com for more information. But it costs money if you did not buy a brand new book. So it's up to you if you want to spend the $30 or $40. It's well worth it because it will help you in class, very much so. And I, on occasion, will do my best to show you these in class. Not particularly online yet. The next slide is talking about the axis tilt. It is very important for you to understand that just looking at this slide, it's the tilt of the Earth, and you'll see how the Sun, because of the tilt of the Earth, the Sun casts its shine and its shadow in a different angle than what you might be used to. And that is what causes the seasons. Okay? And then the next slide shows the real seasons is the axis tilt. Alright? Relative to the Sun. The last bullet is, it's the key to the seasons. Without it, we would not have seasons on Earth. Okay? Next is, does distance matter? Why not? There's a small variation in the distance the Earth is from the Sun, only about 3%. Okay? The two notes that you see here should be considered optional. You don't really need to think too much about them. But the first note I just want to point out the Earth is closer to the Sun in the southern hemisphere in the summer. When the Earth is closer to the Sun, it's summer in the southern and winter in the uh, uh, northern hemisphere, and opposite. Okay. Next slide is how do we mark the progression of the seasons? Um, we define four special points: summer solstice, winter solstice, spring or vernal equinox, fall or autumnal equinox. And I'll leave it to you to look at the slide to understand when those two occur. But let me just point out one: the summer solstice on the left of the slide. In the northern hemisphere, you'll see that the North Pole is pointing toward the Sun by 23.5 degrees. It's leaning toward, like bowing toward the Sun. And because of that, it's facing the Sun, and you see that the Sun is shining in the North Pole 24 hours a day. But look in the South celestial sphere. The Sun is not shining in the south. It is dark 24 hours a day. During the summer solstice, that is the case. Alright? So that is why we have summer at this time of the year in the northern hemisphere, and winter in the same time of the year in the southern hemisphere. The summer solstice occurs on September 21st or 22nd, depending on the time of the century we're in, or the millennium. Okay? And then you can take it around this figure to the fall equinox. The fall equinox occurs in the fall. Okay, you with me? Let me back up. The summer solstice occurs in June 21st or 22nd. The fall equinox occurs in September 21st and 22nd. Winter, December 21st, 22nd. So it's not winter yet. It feels kind of cold to me today. The spring equinox, April 21st, 22nd. Alright, moving on. So we recognize the solstices and the equinox by looking at the sun's path. And I'll leave this slide to you to look at and to use as a frame of reference in the lectures. Moving on. You'll see that in the northern hemisphere, like in Alaska, the next slide shows you that the sun never completely goes below the horizon during certain times of the summer in the northern hemisphere, because the Earth is tilted toward the sun at this time. So the length of day is 24 hours. Next slide shows you something that you may not be aware of, but the Earth wobbles. In planetary geology, we call that the precession of Earth. The Earth wobbles. So, keeping what I just told you in mind with that tilt of the Earth, knowing that the Earth is starting to ever so slightly in a 26,000 year period, 26,000 years, the Earth wobbles. So it's starting to stand up. Ever so slightly, that 23.5 degree tilt is going to be reduced over a very, very long period of time. As it continues to stand up, more and more sun will be cast on both sides of the hemisphere. The northern hemisphere will get more, the southern hemisphere will get less as time goes by. It's called the precession of Earth. So as the Earth starts to sit up, it starts to warm up in the northern hemisphere. You with me? And in the southern hemisphere, depending on the time of the year. Alright, so in recap, we told you that the tilt of the Earth is the most important part regarding the seasons, not the distance from the sun. Alright, and then we marked progression of the seasons: summer, winter, fall, spring. Alright, winter, spring, summer, and fall. Okay, so we've also learned the Earth's axis change with time. Let me say that again. Winter, spring, summer, and fall. Alright, sounds better, right? A little better? Quiz time! Next slide. Who's the most interesting instructor at Wayland Baptist University? Yours truly. Alright, you can ask the fruitcake lady. I'll let you do that later. I don't have the link for you. Maybe I'll show you in class when we meet. So I have the quote, another quote of the day from the Bible. Hebrews chapter 3 verse 4. Every house is built by someone, but he who built all things is God. That is so true. I have links for you to talk about how things end. The final touchdown for Shuttle Atlantis. The fact that we have volcanoes still erupting on the Earth. A night in Ecuador. You can go to those links. They should work for you. All right. Something that I love is electrical engineering. I did that for 14 solid years for the government. Um, Now I'm more in programming than in specific nerdy electrical engineering, but I like to do some humor. Here's one of my latest projects. Um, I hope if you need some help that you come to me for electrical engineering advice, because this is my portfolio here to show you how good I am. Not. Okay, if you do take advantage of masteringastronomy.com that the authors have provided to you, I have established an online class just so you can do the tutorials and take the quizzes, learn some more, all the interactive figures that the book is linked to. You can use this course ID, alright, and I gave you the link on that slide. Next slide is section 2.3 of my lecture. Alright, the moon, our constant companion. Why do we see phases of the moon? We are going to stop this lecture at this point, and I'm going to give you another lecture on the moon. Thank you for your time. It's been approximately 47 minutes. I'm going to give you some time to take a break, and we'll get back to this lecture on the moon, continuing chapter 2.